This is video 10D. In this video we're going to talk about changes of state. So we've gone over some of these terms: vaporization, evaporation, condensation, freezing, melting, sublimation. I just want to make sure that you're clear on all of these terms. So the difference between vaporization and evaporation: if I spilled some water on the floor of the chemical room, it would eventually evaporate. It will eventually change from a liquid to a gas, but the key is that that happens well below the boiling point. The water on the floor doesn't start to boil and change from a liquid to a gas. But if I was making spaghetti and I had a big pot on the stove and I'm boiling water, that water is actually vaporizing. It's changing from a liquid to a gas at its boiling point. There's a slight difference between vaporization and evaporation. Is it below the boiling point, or is it at its boiling point? Condensation, from a gas to a liquid. Freezing, liquid to solid. Melting, solid to liquid. Again, if you're confused about some of these terms, you need to know all 6 of them. Go back a couple slides, go back to the last video, and make sure you're clear on all 6 of these terms. Our new term for video D is vapor pressure. Now, the definition kind of makes sense because it's the pressure of the vapor. So if we're looking at this diagram on the right, this is a liquid. This would be the gas form. So it can evaporate, it can change from a liquid to a gas without even boiling. So the vapor pressure, if I would put a pressure sensor right here, the vapor pressure will be what's recorded by that pressure sensor exerted by the vapor trying to get out of the liquid phase. Molecules, you can see from this picture, gradually try and escape from the surface of the liquid into the gas phase. As molecules build up above the liquid, they become more numerous in the gas phase. Sometimes they'll condense, usually against the walls because they're cooler. You can watch this happen if you put a lid on your boiling spaghetti. It'll condense and fall back into the liquid state. So this rate remains constant. Some liquid is trying to escape to a gas. Some gas is going back to a liquid. It's a constant state of vaporization. It's said to be at equilibrium. It's balanced. The rate of vaporization, going from a liquid to a gas, is equal to the rate of condensation, gas going back to a liquid. We're not changing our number of molecules. Our system is closed. That would change if you take the lid off of it and steam comes out. Then you're changing your gas molecules. You're changing the number of particles in your whole system. So this is a dynamic situation because they are both changing at the same time. Now, what does this mean? Vapor pressure. If you think, and maybe ladies, you'll be more familiar with this than the gentlemen. If you think about nail polish remover, how quickly does nail polish remover dry? For you guys who've never used nail polish remover, it dries very, very quickly. So liquids, such as nail polish remover, that have a very high vapor pressure, they evaporate very, very easily, very, very quickly. If you spill it, it's gone. This term is said to be volatile. If you have a volatile substance, it's going to evaporate very quickly. Vapor pressure decreases, it goes down, with increasing intermolecular forces. Why? If you increase your molecular forces, it's harder to break apart, and fewer molecules will actually evaporate. If it's a bigger molecule, if it's more polar, remember that scale, 0.5, 0.5 to Yeah, that's coming back. Review for final exam. Dipole-dipole forces are stronger yet. Hydrogen bonding, which is an example, water, takes a pretty long time for water to evaporate because it has high intermolecular forces. So, vapor pressure increases significantly as you increase the temperature. Why? What's happening with our particles if you increase temperature? Think about the gas unit. If you increase temperature on the gas unit, the particles want to move faster. If your liquid starts boiling, you're closer to that vapor phase anyway. They measured this with a barometer. We're not going to get into that. We're not going to get into this equation. You should just know why and how this happens. If you're more volatile, you're going to have a higher vapor pressure. If you increase your temperature, you're going to have a higher vapor pressure. You're closer to that gas phase. Your particles are moving faster. They can escape more easily. We're going to look into a phase diagram, but if you think back on your phase changes, where my plateaus were at the melting point and the boiling point. The normal melting point is the temperature at which the solid and the liquid are in equilibrium, so it's balanced between solid and liquid. Both of those phases are present at the same time, and our constant pressure still, just like the gas unit, is 1 atmosphere. Same thing with the normal boiling point. Normal boiling point is where you have both a liquid and a gas at the same time, always at 1 atmosphere. Standard pressure, standard pressure, standard pressure. The temperature at which vapor pressure of the liquid has to be 1 atm. So vapor pressure, boiling point, that balance between liquid and gas phase. So I have part liquid phase, part gas phase. Now there are some substances that can be supercooled, so the liquid can stay a liquid below its normal freezing point, and it can be superheated, so it can still be a liquid even above its boiling point. How does this happen? Well, we're going to have to change the pressure here. It wouldn't be at 1 atmosphere. So 1 atmosphere is always the normal, and again, this constant is listed under your thermo section on your periodic table. Phase diagrams. Here's what we're going to be looking for. A phase diagram shows the relationship between pressure, temperature, and phase, or state, right, solid, liquid, or gas, in a closed system. You will be asked to label the critical temperature, which is the temperature above which you cannot be liquefied. The critical pressure, which is the pressure required to liquefy the gas at the critical temperature. We'll get into all this. The critical point, which is where the critical temperature and the critical pressure meet, where the liquid and vapor have the same density. You can't really tell the difference between a liquid and a gas at this point. And you'll also be able, or be required to label the triple point, which is the exact temperature and pressure where you can see gas and liquid and solid all at the same time together. So it's both boiling and melting at the same time. Here's what a phase diagram looks like. You have temperature on the x-axis, and we have pressure now on the y-axis. These would be low temperatures. These would be high temperatures. These would be low pressures, and this would be high pressure. So, at a low temperature and low pressure, I usually exist in the solid phase. Low temperature, low pressure, This is the solid phase. On the flip side of that, if you're at very high temperatures, this is the gas phase. Each phase diagram has its own division, but they all kind of look the same. You have solid at the low temperature, gas at the high temperature, and liquid would fall in the middle. So this line here between the solid and the liquid phase is where both solid and liquid are present at the same time. When I have both solid and liquid present at the same time, if I increase the temperature, I'm going to melt, and if I decrease the temperature, I'm going to freeze. So this is our melting freezing equilibrium line. Same thing here between a liquid and gas. I have liquid and gas at the same time. If I increase the temperature, I'll change to a gas. If I decrease the temperature, I'll change to a liquid. This would be my boiling and condensation point. Similar to this being melting and freezing. And this equilibrium point is where solid and gas both exist at the same time. Solid-gas equilibrium is either sublimation if you are increasing the temperature, or desublimation or deposition if you're decreasing the temperature. So we have all our equilibrium lines, and the couple points that you'll need to be able to identify. One is right here. This is our triple point. This is where solid and liquid and gas all exist at the same time. It would happen at specifically this pressure, whatever that number might be on the diagram, and this temperature right here. Triple point, where solid, liquid, and gas all exist at the same time. The other point that you'll need to identify is the critical point. The critical point is where we can't really tell by looking at it if it's a liquid or a gas. And that critical point would happen at this temperature and this pressure. Again, if our graph had numbers, you'd be able to read that off the graph. So this is a typical phase diagram where the solid phase is more dense than the liquid phase. Here's a second example of a phase diagram. This phase diagram is actually the phase diagram for water. If you look closely and we compare the last diagram with this one, you'll see now that the freezing melting equivalence line right here between solid and liquid actually bends backwards. The other one kind of leaned to the right. This one leans to the left. This is part of the reason why ice melts on top of water. The solid phase is actually less dense than the liquid phase, so the ice will float on top of the water. The normal melting point is less than that. The normal melting point, again, normal, 1 atmosphere. The normal melting point, which is right here, is actually less than the triple point. Therefore, solid floats on liquid. Again, here's another example. You'll be able to identify, or you'll be asked to identify all these pieces, where the solid phase is, where the liquid phase is, and the gas phase, remembering that temperature in degrees Celsius, low temperature is solid, high temperature is gas, liquids are in the middle. You will be asked to identify the triple point. On this specific graph, we can give data. So the triple point for water, specific data, is at 4.58 torr and 0.0098 degrees Celsius. So I can read things off of this chart now that I have numbers. The normal melting point, which is between solid and liquid phase, normal melting, 1 atmosphere, is at 0 degrees Celsius. And the normal boiling point between liquid and gas phase for water is at 100 degrees Celsius. You will also be asked to identify the triple point, where you can find solid and liquid gas all present, all at the same time. And you will be asked to identify the critical point. Again, the critical point is where you can't tell the difference between the liquid and the gas phase. If there was more data, you could give a specific temperature for the critical point and a specific pressure for the critical point. So, what kind of questions am I going to ask you about these phase diagrams? Well, here's a good quiz or test question. Label what is happening at each point on the diagram. Point A is right here. Point A is the triple point. The triple point is where you have solid and liquid and gas all at the same time. Point B is in between the solid liquid phase. So what's happening? I'm either melting if I'm going this way, or I'm freezing if you're going this way. Point C is always going to be solid phase no matter what. Pause the video, finish these. I'll give you the answers on the next slide. Here are the answers for what's happening at points A through H. Mark any of these that you have questions about so we can talk about them when you come to class. Some other potential questions. On this phase diagram, a solid can be present at which points? We know a solid can definitely be present here. At B, you have solid and liquid in equilibrium. At A, we have solid, liquid, and gas all together in equilibrium. And at E, you have solid and gas equilibrium. So a solid can be present at A, B, C, and E points on this diagram. So my answer would be 4. A substance described by this phase diagram under normal conditions. Remember, normal conditions, pressure is 1 atmosphere. Normal conditions. At 1 atmosphere, I can either be in the solid or the gas phase. So, normal, standard conditions for the thermo unit are 1 atmosphere and, this time we change it a little bit, 25 degrees Celsius. Check on your periodic table, it should be listed. The standard for this unit is 1 atmosphere and 25 degrees Celsius. So if 5 degrees Celsius is right here, anywhere above 5 degrees Celsius, this substance would be a gas. Part 2 to this question, a substance described by this phase diagram under these conditions, 5 degrees Celsius and 5 atm. 5 degrees Celsius and 5 atm. Here's 5 degrees Celsius. Here's 1 atmosphere. So 1 atmosphere, anywhere above 1 atmosphere, if this is 5 or if this is 5, wherever 5 might be on this graph, is always going to be in the solid phase. How about this question? When heated at standard pressure, starting at 10 degrees Celsius, this substance would do what? When heated, so my temperature is going to increase, starting at 10 degrees Celsius, 10 again can be anywhere above 5, under standard pressure, that means I'm at 1 atmosphere. 1 atmosphere and 10 degrees Celsius puts me about here on the graph. If I heat this substance, keeping pressure the same, I'm going to increase my temperature. What happens to the substance? It increases its temperature without a phase change because it never goes out of that gas range. Again, part 2. What if you start at 0 degrees Celsius and 1 atmosphere? Still starting at 1 atmosphere, but now I'm at 0 degrees Celsius. That would put me about here on the graph. When I increase my temperature now, I'm going to hit this line. What does this line do right here before I increase the temperature? I'm changing from the solid to the gas phase, solid to gas. It's going to sublime. Being specific, it's going to sublime at 5 degrees Celsius. Then it will continue on in the gas phase. So it's going to go from solid to gas. It will sublime at 5 degrees Celsius. Write down any questions you might have for anything in this unit, for anything we need to review. Video A, B, C, D, anything about entropy, enthalpy, phase diagrams, the phase change calculations with how many steps they might have in each problem. Write down any questions you might have. Come in, we'll talk about them next class. The link that you're going to see to end this video, the YouTube video, is going to show you what it would look like at the triple point. Triple point, again, is where solid and liquid and gas all exist at the same time. So it's melting and it's boiling all at the same time. Keep your eyes peeled, see if you can see it.